All right, 5.1, Introduction to Polynomial Equations and Graph. So, polynomial function. Example of a polynomial function, something like this. Maybe you have some f of x equals 3x to the fifth plus square root 2x cubed minus 5x squared plus 2. Okay, just made this up. Now, you might be asked, what is the degree of the polynomial? To determine the degree, what do? We look at the highest powered term, okay? So when we look at this as a variable polynomial in x, so I'm looking at my whole polynomial here. The highest degree term looks to be x to the fifth. Therefore, this is a degree 5 polynomial. Now, the lead term, this is, the lead term is what determines the degree. My lead term here is 3x to the fifth. But if you're asked for the leading coefficient, here, this is the number in front of the variable. That leading coefficient happens to be 3. Okay? Now, in general, this is going to look scary, but the general nth degree, so this means their lead term is x to the n, right? So nth degree polynomial function, this is f of x equals a, and we'll just say sub n, x to the n plus a n minus 1, x to the n minus 1, plus blah, 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 all the way down to x to the 1, x, a to the 1, x to the 1, plus a to the 0. And if you want to put x to the 0, you could, but what is x to the 0? This is just 1. So that last term is just a constant. Okay. All right. So the lead coefficient here, we look for the lead term. It's this term right here. That's the term that dictates what how the rest of the polynomial is going to behave in overall behavior. And so look at that. The lead coefficient is an. All right. Things to know about polynomials: they're smooth, continuous, and there's no breaks. No breaks. The domain for polynomials is negative infinity to positive infinity. Okay? Each power is positive or non-negative integers. Okay, so when we look back at this example, x to the 5, 3, 2, those are all positive integers. Now, this square root of 2 right here, that's a coefficient. We're not talking about the coefficient, we're talking about the exponents here. Okay? Sometimes it's helpful to see things that are not polynomials to get an idea of what things that are polynomials. So non-examples, so not polynomials, include f of x equals -3 square root x plus square root 3 x squared plus 5. Why is this a non-polynomial? Well, this exponent here, that's good. Okay, no big deal there. It's just fine to have 5 as a constant. No big deal. That's your a0 there. That's good. The issue is this bad boy right here, x to the 1/2. Now remember our properties. Okay, so x to the 1/2, that's an understood 2 here. There's only one x inside. The index is the denominator of my rational fraction. Remember your rider and the horsey, right? Who goes in the house? The rider. Who goes outside? The horse. Who goes on top? The rider. Who goes underneath? The horse. That's x to the 1/2. Okay? So if you look at this, this is not a positive integer, therefore it is not a polynomial. Okay. Take another one, g of x, maybe it equals 8x to the 3 minus x to the -1 plus 2. Okay, 8x cubed, that's good. 2, that's just another number. Here's our issue right here, -1 in the exponent. Think about this. -1 in the exponent, that's the same as saying 1 over x to the +1. Okay, remember negative exponents, we do the reciprocal, flip it. Okay, this graph, if I were to graph this in my calculator, guess what would be a bad value for us? X equal to 0. Why? Thou shalt not divide by 0, right guys? So can't divide by 0 here, so 0 is not in our domain. That directly contradicts our idea for polynomials, so not a polynomial. Okay, not a polynomial. All right. Here's an example. Solve the polynomial equation. Seems like a good test question. Solve the polynomial equation. So x cubed minus 65x squared plus 64x equal to 0. How do we solve this? Okay, let's think about this for a second. I have an expression set equal to 0. Okay, first thing I think of is factoring. First step in factoring, step number 1, GCF. Always GCF first. So GCF, I can pull an x out of each of those. If I pull an x out of each of them, I have x squared minus 65x plus 64, all equal to 0. Okay, the x is factored as much as we can, but guess what? This is a trinomial. When I think trinomial, I think T-chart. 3 terms. T-chart. So T-chart, I want something that adds to -65 and multiplies to 64. Is this possible? 64 times 1, that's adds to +65. That's close. So wait, let's just do -64 times -1, and we get -64 plus -1 gets me -65. That's exactly what I want. Bingo, there's my answer right there. Okay, since my a is 1, this one's one of those easy ones to factor. It's going to be x minus 64, x minus 1. And don't forget your x that you had up here. Keep bringing it down. Okay, so how do I solve? I use the zero factor property, which says if I have a number times another number, I get 0, then that means the first number or the second one is equal to 0. Same thing works if you've got another number here. I just keep running it through with each factor, set each one equal to 0, solve for x. No biggie. Usually I just do the first one and then tell my students to do the rest of them, but since you're not here, I guess I'll do them for you. Add 1, and you get x equals 1 here. All right, cool. So my solution, x equals 0, x equals 64, and x equals 1. Next one. Does x equal -6 solve the following polynomial equation? And here's the equation. Let's say -22 x squared plus 8x equals 4x cubed plus 24. All right, how do we check to see if something solves an equation? Everywhere I see an x, I'm going to replace it with -6. The key here is to put a parentheses around what you replace with. So I've got -22, and then in parentheses, what am I going to put? -6, and I'm squaring it, plus 8 times parentheses -6 equals 4, and then in parentheses cubed, we've got -6 plus 24. Now, in order for this to be a solution that solves, I need the left side equal to the right side. So we just need to plug this into the calculator. So go to your calculator, type this in. Okay. So when you go to your calculator, you type it in, -22 times -6, close parentheses, square it, plus 8 times parentheses -6 square. If you put your parentheses, all you have to do is type it exactly how it's written. I get -840. Now let's do the other side, the left side. 4 parentheses -6 close parentheses cubed, and then what? Plus 24. Hit enter, and I get -840 again. Therefore, we got ourselves a solution to the equation. -840 equals -840. That's what we'll be looking for. Yes. Okay, that is a solution. Cool. All right, let's talk about end behavior. I know we've done this a couple of times in my class, but it keeps popping up over and over. End behavior of a polynomial function. End behavior of a polynomial function. F of x equals an x to the n plus an minus 1 x to the n minus 1 plus blah 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 all the way down a1 x1 plus a0. Now, this is a lot of stuff going on here in terms. This essentially, when I'm talking about end behavior, the biggest term dominates. Sorry, I didn't turn my phone on silent. The biggest term dominates at infinity. So the biggest degree term is an x to the n. for x going to infinity or x going to negative infinity. Okay? Basically, when I go to the right real far, and this means go to the left pretty far. Okay? So, let me break this up. If an, x to the n, we've got an positive, right? And n is even. N is even. What's that going to look like? If an is positive and x to the n is even, you're going to have n behavior that's going to infinity, positive on both sides. Now, what happens in between is anybody's guess. But the n behavior, you're going up on both sides. Now, if an is negative, okay, if an is negative, instead of being going up positive, we're going down negative on both sides. Okay? And what happens in between, who knows? But we do know the n behavior is negative. And the way I told you how to memorize this was even. If I have an even degree, think even is the same. It's the same. If one side goes down, the other side's got to go down. If one side goes up, the other side has to go up. Even is the same in behavior. If it's a positive number, when I'm positive, I'm smiling. I'm going up on both sides. If it's a negative number, less than 0, negative, I'm frowning. I'm going down on both sides. Okay? Now, instead of being an even degree, you could have an odd, n odd. And if an is positive and it's odd, what does that tell me? On right-hand behavior, I end up at positive infinity. But odd means opposite. That's what I want you to think, opposite. So if the right-hand side goes up, the left-hand side goes down to negative infinity. So what happens in between, that's anybody's guess, depending on what the polynomial, the other terms are. But eventually, it goes up to positive infinity. However, if an is negative, then the right-hand behavior is going to negative infinity. And since it's opposite, the left-hand behavior has to go up to positive infinity. And like I said, it's anybody's guess as to how it behaves in between. Okay? So that kind of summarizes your n behavior for you. All right? So it's a summarization of n behavior. Now, for the second part of 5.1, okay? Heading into some new territory here, but not really super new. Let k be a number such that if I plug that number into a function, I get 0. Then what does that mean? Then k, that number I plugged in, is a 0. So this is a definition for what a 0 is. So if you're ever asked to find a 0, basically you're trying to find a number that when you plug it in, it equals, the output is going to be 0. Okay, it's a root. 0 is a root, solution, etc., 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 to equation. Okay, so I want you to find the zeros of the polynomial function f of x equals x cubed plus 3x squared minus x minus 3. All right. Now, how many terms, okay? How many terms? When I look at this, I have 4 terms. I have 4 terms. Now, first step in factoring is GCF. Is there anything in common between all 4 terms? When I look at all these 4 terms, some have x's, some don't have x's, so can't pull an x out. Some have coefficients. Some are just a constant. Well, 3 and 1, there's nothing in common but 1, so there's really nothing we can pull out for greatest common factor. So 4 terms, I should think factor by grouping. Does this always work? No, but it's a good place to start. Okay, factor by grouping. Factor by grouping. Group the first 2. Group the second 2. And what has to be in the middle? Make sure you have your plus sign in the middle. Okay? Now, when I look at this, my first group, I can GCF, I can pull out an x squared. I have x plus 3 left inside. For this next one here, I'm looking at it. I want it to match this. How do I make it match it? I need to pull out a -1. If I pull a -1 out, what do I have left inside? X plus 3 left inside here. Okay? So, I have an x plus 3 factor and an x plus 3 factor in both of those. I'm going to GCF again, and I'm left with x plus 3. And then what's left? An x squared and a -1. Now you may think that you're completely factored here, but you're not quite there. Could you solve this? Could you solve it if I have it set equal to 0? Sure, okay. But this right here, this is a difference of squares. So this is actually equal to x plus 3 times, and my difference of squares, how do I do it? I square root both pieces and see what I get. I get 1 and I get x. So that gives me x plus 1, x minus 1 for my difference of squares. Remember our formula? A squared minus b squared is a minus b, a plus b, or vice versa. It doesn't matter. Multiplication is commutative. Okay? So, what have I gained from this? It says find the zeros. What are the zeros? That's where if I plug in a number, I get 0. So how do I find the zeros? I take f of x and I set it equal to 0. What is f of x? F of x is x plus 3 times x plus 1 times x minus 1. That's the factored form of this polynomial right here. Okay? And I set it equal to 0. So now that it's equal to 0, all I need to do is set each factor equal to 0 and solve for x. So subtract 3 from both sides, I get x equals -3. Subtract 1 from both sides, I get x equal to -1. And add 1 to both sides, I get x equal to 1. Right there. Okay, get x equal to 1. All right. Let's talk about multiplicities. Let's talk about multiplicities. Multiplicities of 0. Multiplicities of zeros. say I have f of x function equals x minus 1 times x plus 2 squared, and then let's do times x cubed. Okay? Talk about multiplicities of zeros. Well, this form for us is really nice because it's already factored. All right? When I look at this, I have only one factor. Okay? It's just one factor, x minus 1. So the multiplicity right here, how many copies there are, you can think of multiplicity as how many copies. Okay. This is a multiplicity equal to 1. There's one factor here. And if I solve that, x minus 1 equal to 0, I get x equals 1. So it's a multiplicity of 1 at the 0, x equal to 1. Okay? For this next one here, how many x plus 2's do I have? Technically, I've got x plus 2 times x plus 2. That's what this 2 is telling me. There's 2 copies. So the multiplicity here is equal to 2. Okay? Now, how do I find the root? I set x plus 2 equal to 0, solve for x. So it has a multiplicity of 2 at x equal to negative 2. Okay, at x equal to negative 2. And then this last one here, this has how many copies of itself? Well, this is technically x times x times x. So that has 3 factors. So what do you think the multiplicity is? The multiplicity is equal to 3. Multiplicity of 3. So I take x, the factor x, and I set it equal to 0, solve. That's pretty easy to solve. So it has a multiplicity of 3 at x equal to 0. Okay? All right. Now you might be asked to find the degree of f. Okay, find the degree of f. Now, there's 2 ways to do this. The hard way or the easy way. All right? So it's your choice what you want to do. You can either do it the hard way and multiply all this out and look for the lead term and figure out the degree of that term, and then that's the degree. Or 2, which is my suggestion. Okay? Look at the multiplicities of the terms. How many multiplicities? 1 here, 2 here, 3 here. When I look at this term, there's a 1. It's a degree 1. And there's only 1 of them. So that is degree 1 for that first term. This is a degree 1, and there's 2 of them. If I multiplied this out, x times x is x squared. That's a degree 2 term. And then I look here at this last one. There's 3x is x times x times x. That's x cubed. That's a degree 3 term. And to figure out the degree of all of them, remember when I multiply things, I add the exponents. We're talking about exponents here. I add 1 plus 2 plus 3, and I get 6. So the degree of f is a degree 6. It's a degree 6 polynomial. Right? If it's an even degree means that they're both going up or they're both going down. They're both going down. Okay? So let's talk about how we're going to graph this. All right, so let's just throw in a little sticky note. So Let's graph this. Okay. So where are my roots at? My roots are at 1. My roots are at -2. My roots are at 0. So these are critical points here. Okay. The graph. Now, either both are going up or they're both going down. Okay. So we got to figure out my end behavior to graph this. End behavior. End behavior. How do I look at the end behavior here? Well, I need to know that term. I know it's a degree 6. I need to know, is my number in front positive or negative? If it's positive, then I'm going up both ways. If it's negative, I'm going down both ways. Okay? So if I look at this, I have an x positive 1 coefficient. I have an x, a positive 1 coefficient, and I have an x cubed positive 1 coefficient. 1 to the 1 is 1. 1 squared is still 1. And 1 cubed is 1. 1 times 1 times 1, that's all equal to 1. So my term here is positive. This is a positive, so I know that my end behavior is going to be positive on both sides. Okay. So let's graph this. How do we graph this? Well, we know we're coming down. We're coming down. All right. My first root that I'm going to run into is this -2. Okay. Now, what's going to happen when I get close to my root? The multiplicity is even. The multiplicity is even. Even multiplicity, we're going to bounce. We're going to touch the axis. Okay? We're going to touch the axis. So I come down, I touch it, and then I bounce back up. All right? I bounce back up. Now, we're not worried about how high we bounce. To know that, you either need a graphing calculator or calculus. So we're not talking about calculating relative max and mins here. We're just considering what's the behavior around the 0. Okay, so the first 0 was 2. It's an even multiplicity. We touch, we bounce. Okay. Odd multiplicity. We cross. We cut through the axis. We cut through it. So at x equal to 0, my multiplicity is 3, so that's odd. So I'm going to cut through the axis. But the thing is, I'm going to cut through the axis kind of at a little bend. Okay, I'm going to cut through at a little bend here. Why do I cut through at a little bend? For odd multiplicity, or even, if the degree slash multiplicity of the factor is greater than 1, then we flatten out. That's a question that pops up a lot in the homework. Does the 0 flatten out? So does the degree flatten out? And what does that mean? Well, it might be easier to show you what happens when it doesn't flatten out. So times where it won't flatten out is whenever it's not greater than 1, so it's equal to 1. So multiplicity here at 1 is 1. So something that doesn't flatten out would be like this here. okay? So when I look at this, I see my curve coming in. It's coming into the 0, and then it flattens out. It bounces because the multiplicity is a 2. Multiplicity 2. So it's going to bounce. And I'm coming up, I'm coming up, I'm coming up, and I'm going down. And then I get to my 0 here, and it flattens out and then goes down. So the multiplicity here is a 3, so that means we cut straight through the axis, but we flatten out when we're close to the root. You see the little bend in our curve here? It bends a little bit. But this last one here, has a multiplicity of 1, so there's no flattening out, so it just goes straight through without bending any. Okay, that's the idea. That's the idea. And this is not going to be, that's not sharp. That's just the way my picture came out. It's probably going to be more of a bend, like that. Okay. But there's no bend in here, not flattening out. Okay. No flattening out. All right. So kind of give you a view of the whole problem at one time. Okay, guys, I know this is a lot. We're gonna keep dealing with this. It's not going away. So just watch this video as many times as you need. But let's do a couple more examples. You know what? Actually, I think I might make a new video with a couple more examples to follow up on these concepts. So we'll do it that way. All right, guys, good luck.